In this video, we are going to look into effect of substituents on reactivity and reactions of benzene. A substituent affects reactivity of benzene ring, or in other words, it affects reaction rate of benzene ring. Substituent on benzene ring could be an electron donating or electron withdrawing, and they are labeled here as EDG for electron donating group and EWG for electron withdrawing group. An electron donating group is activating substituent in electrophilic aromatic substitution reactions of benzene. We already covered those reactions earlier. And conversely, an electron withdrawing group, electron withdrawing substituent, is deactivating substituent, and it deactivates benzene towards electrophilic aromatic substitutions. So activating substituent means that benzene with an activating substituent reacts at faster rate compared to unsubstituted simple benzene ring, benzene molecule. And of course, deactivating substituent makes such substituted benzene react slower compared to unsubstituted benzene. Activating substituents exhibit considerable difference in magnitude of the effect that they exert on benzene ring. So we can identify strongly activating, and another class of that we call moderately or mildly activating, and finally weakly activating substituents. A typical substituent that would be strongly or moderately activating has a free electron pair on the atom bonded to the benzene ring. Here are examples of strongly activating substituents. So strongly activating substituents are groups such as hydroxyl group, alkoxy group, amino group, and similar substituents. They exhibit negative inductive effect, which means electron withdrawal, but that effect is relatively minor. It's much weaker compared to positive resonance effect, electron donation through resonance effect. So they activate benzene ring through electron donation through positive resonance effect, and we consider inductive effect to be minor effect. You should note that here halogen atoms are not included. They don't belong to this group. Although they are similar to these substituents listed here, in that they have free electron pair and they exhibit positive resonance and negative inductive effect, in their case, inductive effect is in general stronger in magnitude compared to resonance effect. And so they are actually deactivating. So keep in mind that halogens do not belong here. There is some disagreement about the role of fluorine. Some authors believe, and there is considerable evidence to that effect, that fluorine actually is different from other halogens and it is activating. On the other hand, there is no doubt that chlorine, bromine, and iodine substituents are deactivating. Moderately activating substituents are atoms that we have encountered before as strongly activating. So typically oxygen and nitrogen atoms, but their other substituents is an electron withdrawing group. So they are oxygen or nitrogen atoms that have one bond to benzene ring and another bond to another electron withdrawing substituent. So they are moderately activating because electron withdrawing substituent competes for electron pair, for the localized electron pair. So that electron pair is not completely available for donation to benzene ring through positive resonance effect, as it is being shared. It's being delocalized both to benzene ring and to the other electron withdrawing substituent. Typically that electron withdrawing substituent is a carbonyl group. So esters with oxygen, ester oxygen bonded to benzene ring, or amides with nitrogen bonded to benzene ring are typical moderately activating substituents. And here you have shown resonance structures that show on the left electron donation to benzene ring and on the right electron donation to carbonyl group. Keep in mind that even though oxygen has two free electron pairs, only one of them is in the unhybridized atomic p orbital, and that means that only one of them can be delocalized. Weakly activating substituents are substituents that activate benzene ring through positive inductive effect, and those are typical hydrocarbon substituents substituents such as alkyl groups. Also vinyl group fits into this class, and benzene rings, for example in biphenyl, activate each other. Again, effect is relatively weak, nonetheless it's noticeable, so those are weakly activating substituents. And note that two benzene rings in biphenyl interact only through inductive effect. That means effect that spreads through sigma bonds. Two benzene rings in biphenyl are at 90 degrees to each other. So electron delocalization between these two benzene rings is not possible. So there is no resonance effect between them. A deactivating substituent has either positive charge or high electron deficiency on atom that is directly attached to benzene ring. And common deactivating substituents are listed here in the order of deactivating ability, from the most deactivating on the left to the least on the right. With deactivating substituents, we don't classify them in particular groups like activating it strongly, moderately, weakly, but we can establish some order of activity from the most to the least. And note, it is interesting that most deactivating is quaternary ammonium salt, so nitrogen that is attached to benzene ring, so it's deactivating to strong inductive effect, to strong negative inductive effect. Some other substituents then listed to the right of it, like nitro substituent, nitrile, and so on, are deactivating through negative resonance effect. And it is interesting that least deactivating is another quaternary ammonium compound, or just ammonium salt. But note that this least deactivating substituent has hydrogen attached to nitrogen. And so the reason why it is least deactivating is that these compounds are acidic. These ammonium ions are acidic. And of course, as an acidic compound, it is at equilibrium with its deprotonated form. So there is always a small amount in reaction mixture, there is a small amount of deprotonated form present. Deprotonated form is amino group, NH2, that's activating substituent. And so they react in that form. So the small amount that is present in the activating form is one that actually reacts. And that's why they are considered to be least deactivating. If they couldn't undergo deprotonation, then this substituent would be as deactivating as a quaternary ammonium salt with all alkyl substituents. So that's the difference between the two. Note esters and amides. This is shown here on example of esters. They have been listed previously as activating, moderately activating, and now as deactivating. That depends on the nature of bonding. So if an ester or amide is attached to benzene ring through a carbonyl group, then they are deactivating, because carbonyl carbon is electron deficient, partially positive carbon. On the other hand, if ester is attached to benzene ring through oxygen, then it's activating, because oxygen donates its electron pair to the benzene ring. And conversely, if amide is attached through nitrogen, it would also be activating, because it's capable of electron donation to benzene ring. So make that distinction in a bonding pattern of esters and amides. That determines whether they are activating or deactivating. And finally, halogen substituents are somewhat unique. They are unique in that they are deactivating because inductive effect of halogen is stronger than resonance effect. So halogens exhibit negative inductive effect and positive resonance. And since inductive effect is stronger, they are net electron-withdrawing substituents. The reason for this is in poor orbital overlap of halogens and carbon, halogen p orbital and carbon pi orbital. So for that reason, resonance effect is not very efficient. Electron donation, electron delocalization to resonance is not very efficient. An exception is fluorine atom, because fluorine p orbital, 2p orbital, overlaps very well with carbon pi orbital. And so some authors consider that fluorine, for that reason, is actually activating substituents, while others disagree and argue that fluorine should be still considered to be deactivating because of the high electronegativity. Fluorine has very low tendency to donate electron density. There is evidence on both sides, and there is actually quite strong evidence that fluorine may be activating substituent. On the other hand, there is no doubt that chlorine, bromine, and iodine are deactivating substituents. Besides the effect on reactivity of benzene ring, the existing substituent also affects orientation of the incoming electrophile, the incoming substituent. So it affects regioselectivity of electrophilic aromatic substitution. And so here in this scheme it is shown that existing substituent Z affects orientation of the incoming substituent, incoming electrophile Y. So Y could be attached in the product relative to substituent Z in ortho, meta, or para position. And here are some actual examples. For example, in chlorination of toluene, the existing substituent methyl group directs incoming substituent chlorine into ortho or para position. So products are ortho and para chlorotoluenes. Chlorobenzene in nitration reaction reacts to give mixture again of ortho and para products. So here we have two substituents that direct incoming substituent, incoming electrophile, ortho and para to themselves. Here are some different examples. So benzoic acid in nitration reaction gives meta-nitrobenzoic acid as product. And nitrobenzene in chlorination reaction as a product gives meta-chloronitrobenzene. So we have two substituents that were meta-directing. So from these examples, we can see that substituents in electrophilic aromatic substitution are either ortho-para or meta-directing. Now we are going to look into reasons behind the observed regioselectivity. First, we are going to look at the effect of electron-donating substituent on regioselectivity of an electrophilic aromatic substitution. So we are going to look at weakly electron-donating substituents such as alkyl group, methyl group. So simplest such compound would be toluene, and we can consider reaction with an electrophile such as chloroelectrophile, chloronium ion. So incoming chloronium ion is coming in ortho, meta, or para position, and we are going to analyze each of the three possible reaction pathways. So this would be starting material, and incoming electrophile is coming in any of the three possible positions. So first, in the ortho position, when we consider intermediate, stability of the intermediate cyclohexadinyl cation, we can see that in three resonance structures, one on the left, first resonance structure, involves tertiary carbocation. Obviously, tertiary carbocation is more stable than secondary. So this pathway is going to be somewhat lower energy pathway. It's going to proceed through more stable, lower energy intermediate, so favored intermediate, because carbocation is more stable compared to ordinary cyclohexadinyl cation. This also explains activating effect of methyl substituent. Why this is activating substituent? Because carbocation is more stable. So such benzene ring reacts faster. When electrophile comes in meta position, we can see that in all three resonance structures, carbocation is secondary. So this is actually a default pathway, a pathway in which carbocation has about same energy, same stability as carbocation of ordinary unsubstituted benzene ring. So no particular stabilization. So in this case, reaction is going to be a bit slower because the intermediate is lower or higher energy, actually less stable compared to the first intermediate that was stabilized because one of the resonance structures involved tertiary carbocation. So this would be disfavored pathway. First pathway would be more favored. And then third possibility is for substituent coming in para position. Now note that second resonance structure, middle one, involves tertiary carbocation. So stability of this pathway is about the same as the first one, as ortho. And that from this you can draw conclusion that ortho and para pathways will be preferred and mixture of ortho and para products will be obtained. meta pathway will be disfavored. And so alkyl group is activating because it provides two pathways, two intermediates of lower energy, so faster reaction, and also it's ortho-para directing because those are lower energy pathways. Now we are going to consider another electron donating group, but now we are going to consider a strongly activating group. So we are going to consider phenol as an example of benzene ring with a strongly activating group with hydroxyl group. And now electrophile nitro group is going to come in ortho, meta, and para positions again. And so when we consider ortho substitution pattern, now we can see that there is fourth resonance structure. So intermediate cyclohexadienyl cation is stabilized also through resonance with methyl group, with methyl substituent. And that's extremely stabilizing. Much more stabilizing than simple stabilization of tertiary cation. For that reason, this substituent is strongly activating, because this is much lower energy pathway compared to pathway that was activated simply through existence of resonance structure that involves tertiary cation. So that's why this effect is much stronger and this reaction is much faster. So this explains why such substituents are strongly activating. And also it explains why ortho pathway is preferred. It's very low energy pathway. On the other hand, when substituent comes in meta position, then there is no such resonance stabilization. There is no possibility for stabilization of cyclohexadienyl cation through additional resonance interaction with hydroxyl group, electron donation from hydroxyl group. And then again, in para position, there is such possibility. And you can see middle two structures show resonance stabilization through electron delocalization with hydroxyl group. And so this shows that ortho and para pathways are preferred again. So that's the case with all of the electron donating substituents. Those are lower energy pathways, and that shows why these substituents are activating and also explains regioselectivity, why these substituents are ortho-para directing. Now we are going to look into effect of a deactivating substituent. So our example is going to be nitrobenzene with nitro group as a deactivating substituent. And again, electrophile is coming in ortho, meta, or para positions, in this case iodonium cation. So first let's consider ortho pathway. Now you can see that in ortho pathway the very first resonance structure is extremely unstable. Nitro group is shown in its structural formula, so you can see that nitrogen has positive charge, and in carbocation, in cyclohexadienyl cation, there is positive charge on the carbon attached to nitrogen. So we have high destabilization of this carbocation by presence of two neighboring positive charges. Obviously identical charges repel each other, and so this is highly destabilizing to have one such strongly electron withdrawing substituent on carbocation on carbon that is already electron deficient. So extremely destabilizing interaction, and for that reason this pathway, ortho pathway, is going to be disfavored. This also shows why such substituent is deactivating, because it increases the energy of the intermediate cyclohexadienyl cation, and it disfavors this reaction pathway. So this is certainly disfavored reaction pathway compared to unsubstituted benzene ring. So pathway leading to formation of ortho product is going to be disfavored, and also reaction of compound like this will be slower compared to unsubstituted benzene ring. Now when we consider meta pathway, then we can see that such disfavored interaction, such destabilizing interaction is not present. And so this pathway is going to be a lower energy pathway. It will be somewhat similar to pathway of unsubstituted benzene ring. So lower energy pathway, and certainly refers to ortho pathway. So in this case, meta pathway, simply because it is not destabilized, is preferred compared to ortho pathway. And finally, we can see in para pathway, again there is destabilizing interaction. Middle interaction is destabilizing, just like ortho, because of the presence of the neighboring positive charges, or in other words, presence of electron withdrawing substituent on carbocation. So two destabilizing interactions. So presence of an electron withdrawing substituent will disfavor ortho and para pathways, and for that reason then meta pathway operates as a default pathway. So an electron withdrawing substituent is deactivating and meta directing. We have just gone through rather extensive analysis of intermediate cyclohexadienyl cations to explain regioselectivity of electrophilic aromatic substitution. At first glance, this may appear to be redundant, and that we may be able to apply simple consideration of electron densities on benzene ring as a consequence of resonance effect of substituents. So if you consider resonance effect of an electron donating substituent, such as hydroxyl group of phenol, you will see that it increases electron density in benzene ring in ortho and para positions, and happens to be ortho-para directing. Nitro group decreases electron density in ortho and para positions, and that leaves meta position for attack by an electrophile. So it would appear that simple consideration of electron density on benzene ring as a consequence of resonance could predict the orientation of electrophilic aromatic substitution. But that's actually not the case, even though both consideration of stability of intermediate cyclohexadienyl cations and consideration of electron density on benzene ring as consequence of presence of substituent give the same prediction. One should consider stability of cyclohexadienyl cation, or in general intermediate cation, because that's one that will give correct prediction, and that's one that really determines regioselectivity. In this case, when both effects operate in same direction, give same prediction, we cannot distinguish between them. But in case of compounds where such things would give different prediction, then we can distinguish. In case of compounds like pyrrole or purane, we do not carry out analysis of reactions of these compounds. It's too complex for a course like this, but then prediction is different, and now we know that we should consider stability of the intermediate cation, not electron density. We have seen that electron-donating substituents are ortho-para directing. But question is, when two isomers are formed, in what ratio are the two isomers formed? So studies of simple substituent effects are carried out on alkyl substitute benzenes. And in this case, effect is clearly steric. So in nitration of various alkyl benzenes, methylbenzene or toluene, ethyl isopropyl tertiary butyl benzene, we can see that in case of toluene, ortho-para ratio is close to the statistically expected ratio. It's close to 2 to 1. There are two ortho, one para position, and that should mean 67-33% yield, ortho versus para. We get 62-38. So even in this case, we get a bit less ortho isomer, a little bit more para isomer is formed. And then ethyl ratio is about 1 to 1. So more, in fact, more para isomer is formed than ortho. And then with larger substituents, para isomer clearly predominates. And that's steric effect. That's because of the presence of steric hindrance in ortho isomer. Para isomer forms preferentially. One should keep in mind that this analysis applies only to alkyl substituents. Other substituents, those that are charged and that are capable of other electronic effects and interaction with the incoming electrophile, exhibit other effects, and analysis of ortho-para ratio becomes much more complex, and in some cases even ortho isomers are preferentially formed. We have seen earlier in previous videos that because of lower reactivity of benzene compared to alkenes, we have to use what we call activated electrophiles. Electrophiles that have been activated by complexation with some reagent or treatment with some reagent to be more reactive compared to ordinary electrophiles that are used in electrophilic addition to alkenes. So typical electrophile that is used in electrophilic aromatic substitution is activated electrophile. But that may change depending on substituents on benzene ring. So if benzene ring is substituted, then considerations may be somewhat different. And here is the first example. To carry out sulfonation of benzene ring, we need to use fuming sulfuric acid, solution of sulfur trioxide in sulfuric acid, concentrated sulfuric acid. But if benzene ring is activated, even weakly activated by, for example, methyl group, then concentrated sulfuric acid is sufficient enough to affect sulfonation of benzene ring. So with activated benzene rings, electrophile often doesn't have to be activated. And here is another example. To nitrate phenol, actually we should not even use mixture of nitric and sulfuric acids. We should use dilute nitric acid, either nitric acid that has been diluted with water or maybe solution of nitric acid in acetic acid, but definitely reagent with lower reactivity. The reagent nitric acid and sulfuric acid would actually cause undesired side effects, and actually it would be difficult to stop nitration after first substitution, and we would end up with polynitrated products. And obviously if we want only mononitrated product, we have to use milder reagent. So in some cases, even use of activated electrophiles is not even desired because it would not yield desired products. Here are some additional examples of effect of activating substituents. So for example, bromination of anisole proceeds simply by addition of bromine. And we can carry out reaction with one equivalent of bromine, and then products are or mixture of ortho and para isomers. Simply monobromination occurs. If we carry out reaction with two equivalents of bromine, then dibromination occurs. And product is 2,4-dibromoanisole. Note that 2,4 is formed because 2,6 would be 2 hindered, with three substituents being next to each other. And finally, with 3 equivalents of bromine, we get 2,4,6-tribromoanisole. So, as you can see, using milder unactivated electrophile, we can obtain any product we want. We can get mono, di, or tri-substitute product. Use of activated electrophile in this case would not be desired. First, there is no reason to use it, but secondly, we could not stop at mono or dinitration products. Only trinitration product is obtained. And in fact, this reaction, even with unactivated electrophile, even with bromine itself, is very fast and is typically completed within about 1 minute. So with activated electrophile, it would probably be completed within seconds, and only tri-bromo product would be obtained. Another example of role of activating substituent in electrophilic aromatic substitution is amino substituent. So nitration of benzene ring with amino substituent can be affected by using acetyl nitrate, very mild nitrating reagent. That's solution of nitric acid in acetic acid. So the two react to form acetyl nitrate, and acetyl nitrate is suitable reagent for nitrating amino compounds. So much milder reagent, of course, compared to mixture of nitric and sulfuric acids. With electron-withdrawing substituents, considerations are somewhat different, obviously. First of all, if substituent itself is electron-withdrawing, it may also be reacting with one of the reagents that we are using. For example, Lewis acids are often used to activate electrophiles. But Lewis acid may complex with electron-withdrawing substituent to make it even stronger electron-withdrawing substituent, and that would completely prevent reaction from occurring. Also, we need to consider even effect of such additives, Lewis acids, on electron-donating substituents, because Lewis acid may complex with electron-donating substituent and turn it into electron-withdrawing substituent, convert it to electron-withdrawing substituent. So for that reason, we should use electrophile that is not activated, because if electrophile is not activated, reaction will proceed very well. Substituent itself is activating. But attempt to activate electrophile may result in conversion of activating substituent into the activating one and prevent reaction from occurring. And finally, in the presence of deactivating substituents, some reactions, electrophilic aromatic substitutions, may not occur at all, those that are more difficult to carry out, that ordinarily proceed at slow rate. And typical such reactions are Friedel-Crafts reactions. So Friedel-Crafts alkylation and acylation in general proceed at slower rate compared to other electrophilic aromatic substitutions, and if substituent is deactivating, they may not occur at all. So for example, presence of nitrosubstituents or carbonyl group on benzene ring will render that benzene ring inactive towards Friedel-Crafts alkylation or acylation reagents. But this completes our examination of effects of substituents on reactivity of benzene ring. And next we are going to look at synthesis of di- and polysubstituted benzenes.